Okay, so hi and welcome to my tutorial on graph neural networks here at the workshop on geometry and machine learning. My name is Matthias. I'm a third-year PhD student at the University of Dortmund in Germany, and if you want to reach out to me, you can do that by mail, Twitter, or GitHub. So my research interest involves basically everything around graph neural networks, which is a fairly young and active research area. And I'm also the creator of PyTorch Geometric, which is a PyTorch extension library to ease the implementation of graph neural networks. Okay, so to start my talk, let's look at the current state of the modern deep learning toolbox. And with a closer look, we will see that this is heavily designed for operating on images and sequences, such as audio signals and text. So, for example, images are represented as a grid and can be inputted into a convolutional neural network for tasks such as image classification. On the other hand, sequences can hold information about text or audio, and those can be inputted into an LSTM or transformer network. However, it is fairly unclear on how we can apply deep learning on problems that can't be modeled by a grid or a sequence. And though the main question graph neural networks are trying to solve is how we can develop neural networks that are much more broadly applicable. So the good thing about that is that we have a data structure that can mostly represent everything in the world, and that is a graph. So a graph just holds two information. It holds the information about nodes, which may describe entities or objects in our world. And then there exists edges between those nodes, which model the relationship between those objects. Okay, so to go beyond classic neural networks, we want to develop neural networks that can operate on those input graphs. And you can also think of them as a more general class of neural networks, since we can also represent images and text as regular graphs. Okay, so with a closer look, this does seem rather challenging. And the main challenge stems from the fact that networks are typically very complex. So, for example, networks or graphs can have an arbitrary size, which means that their number of nodes and edges may vary, and they may have a highly irregular and complex topological structure, which is in high contrast to the underlying structure of images and text. In addition, there is no fixed node ordering or reference point, which basically means that our neural networks should be permutation invariant. So whenever we change the ordering of nodes, our model output should stay the same. And as a further challenge, networks are often dynamic, meaning that the overall structure may change over time. And furthermore, graphs may have multi-model features such as different node and edge types, such as users and products and their different relation types. Okay, so to follow up, I just want to give you an impression on why you should learn more about graph machine learning and graph neural networks in particular. So this figure shows the percentage of keywords found for all submitted papers at the ICLR conference from the past 3 years. And as you can see, graph neural networks have both the highest occurrence of keywords as well as the highest overall growth from previous years. And this indicates that graph neural networks are one of the hottest research fields in the deep learning community at the moment. And I personally think that is due to the fact that graph neural networks can be used in so many domains and can enhance those domains by additional relational knowledge. So, for example, it can be used in computer vision to learn about scene composition, or it can be used in natural language processing by the usage of knowledge graphs. Okay, so in this tutorial, I will first cover some basic concepts like what is learning on graphs and what are the typical applications. And after that, you will learn more about what are graph neural networks. And in particular, you will learn some basic formulations of graph neural networks for a given task at hand, such as relational reasoning or 3D shape analysis. In the next topic, I want to talk about the emerging field of relational structure discovery, where you find out about entities and their relations in our world completely from scratch using graph neural networks. And in the second part of this tutorial, I will cover how to implement graph neural networks with the PyTorch Geometric library. And here I will cover topics such as implementing message passing GNNs and how we can generate mini batches of graphs with potentially different sizes. I have also prepared some Google call-ups which I will run through, and I've also prepared one for a small exercise which you can do after watching this talk. Okay, to get started, we first need to understand what learning on graphs exactly mean. And here the basic goal is to map nodes or entire graphs into an embedding space in which they can be distinguished for a given task at hand. For example, we might have a data set of graphs and we want to classify those graphs based on some structural properties of the graph. And for this, we would first embed each graph into an embedding space, and we would require embeddings of graphs to be distinct if their classes do not match. So more formally, a graph can be either given by a tuple of a node set and an edge set, or by a squared adjacency matrix which holds an entry of 1 if there exists a link between the respective nodes, and 0 otherwise. And furthermore, there may exist additional node and edge features, and along this talk I refer to X as multidimensional node features and to E for multidimensional edge features. To follow up, I would like to present you a certainly non-exhaustive list of applications in which graph neural networks can be applied. So first, of course, with the sheer amount of data in social networks, applied machine learning on those graphs is highly attractive. So one could think of use cases for recommender systems for users based on activities of friends, or tasks such as predicting a certain friendship relation. Next, there is also a lot of interest in applying GNNs to protein-protein interaction networks, or use them to embed whole molecules. Here, tasks include the prediction of protein functions or predicting certain properties of a molecule, for example, if a molecule is toxic or not. There is also a lot of interest in graph generation for molecules for tasks such as drug discovery. Another major field is 3D shape analysis, which can also be tackled by graph neural networks that operates on 3D meshes. You can also find graph neural networks applied in the field of human pose estimation, where graph neural networks can help to identify the relationship between human body joints. Graph neural networks can also be used for visual scene understanding, where you know about objects in a scene and want to infer their relations. For example, one could ask the question whether a person sits on top of a motorbike, and graph neural networks are a good fit for that. There is also a certain interest in applying graph neural networks in physical systems, like understanding the dynamics of objects and how they affect each other. And last but not least, graph neural networks are also applied for tackling the task of autonomous driving, where the surrounding of a car is scanned and processed to a point cloud, in which we can detect cars or other persons. Okay, so what are graph neural networks? And in my opinion, graph neural networks can be seen as a generalization of convolutional neural networks to highly irregular structure. So, for example, in graph neural networks, the concept of locality is a central topic. And in general, we want to learn local patterns of the graph. And while we go deeper, we want to extract more and more global information. And second, we want these learned local patterns to be universally applicable. And this can be done by the concept of weight sharing, so that learned patterns are generalizable to unseen nodes or unseen graphs. And this leads us to the following basic formulation for graph neural networks, which is in fact heavily inspired by the concepts of convolution. So a graph neural network is defined to learn intermediate representations of nodes instead of pixels. And we do so by repeatedly transforming and aggregating node representations from their neighbors. Okay, so this procedure can be described more formally by the concept of message passing, where neighboring nodes exchange messages to update their representations. So first, each neighbor W of a node V sends a message along its edge, and this message might be based on the target and source node representations HV and HW of a layer L-1. Next, these messages are aggregated across all neighbors. And here it is important to note that this aggregate function is typically modeled as a permutation invariant function, meaning that its output does not depend on the ordering of nodes. And typical examples for permutation invariant aggregations are sum, mean, or max aggregation. And last, the output of the aggregate function is used to update the hidden node representation of a node from the previous layer. So there are a lot of graph neural networks proposed in literature, and they basically all follow the simple message passing scheme, but they just implement the functions message, aggregate, and update differently. Okay, so for learning meaningful patterns in the graph, the message passing functions need to be trainable and differentiable, but each node uses the same function for updating its node representations, meaning that the set of parameters is shared across all nodes. And in the graph neural network, these message passing operators are typically stacked and enhanced by nonlinear activation functions, just like in traditional GNNs. So for example, given an input graph, we apply a message passing phase to enrich the feature representation of each node by its neighbors based on their input features x, followed by some activation function. And now each node holds the information about the node itself, plus the aggregated information of their direct neighbors. And in the second layer, we again pass messages to neighboring nodes and aggregate them, meaning that each node now contains information about itself, plus its two-hop neighbors. And doing that so on and so forth, a node has aggregated its L-hop neighborhood information after exactly L layers. And this representation can be used for a downstream task. So for example, we can use the final hidden representation of a node for downstream tasks such as node, graph, and link prediction. So for node classification, we can use a classifier such as an MLP on top of each node embedding. And for graph classification, we need to somehow aggregate each node embedding into a global graph representation. There are multiple ways to do this, and by far the most common one is to simply add each node embedding up before inputting it into a final classifier. For link prediction, we can use pairs of node embeddings to predict the existence of an edge. So, for example, we can concatenate node embeddings before inputting them into a classifier. And here it is important to note that the training of node embeddings happens in an end-to-end fashion in conjunction with the final classifier. And this way, node embeddings can search for features in the neighborhood around each node that might be relevant for the specific task at hand. So let us now look into specific implementations of the message passing scheme. And by far the most popular implementation is the following formula, which can be found in numerous papers with only slight variations. And this formula updates the node embedding of a node V based on its representation itself and all its neighboring node representation HW. And typically, neighboring node features are first normalized before they are aggregated together. And this is here indicated by the usage of sum. And afterwards, the aggregated output is transformed based on a learnable weight matrix and combined with the central node information based on a simple skip connection. And finally, the output is sent through a nonlinear activation function. So this formulation indeed follows the message passing scheme presented earlier. It sends normalized node representations as messages, it aggregates them together, and it finally updates the central node by the usage of skip connections and transformations. And as I said earlier, this is the most commonly found formula for GNNs, and there only exist minor differences based on the normalization coefficient C. And this normalization can be either static, so C is always equal 1. It can also be structure dependent. For example, it normalizes messages based on the node degree. And furthermore, it can also be data dependent, meaning that the normalization coefficients are learned in an end-to-end fashion. And this is usually framed as attention, meaning that a node can attend to neighboring nodes that may have the highest amount of valuable information. However, the previous implementation has some weaknesses which the following implementations are trying to address. First, the previous formulation models an isotropic transformation, and that means that all the nodes were transformed equally based on the same single weight matrix. And to model an anisotropic transformation, we can, for example, use a transformation based on an MLP, which takes in the central node representations and the difference between the central and neighboring node representation. Another formulation may allow for learning on graphs with distinct edge types, for which we may use different weight matrices dependent on the edge type R between the node V and the node W. And for graphs for which we have rich edge features, we may want to transform them based on their specific edge features. And as you can see, there exists a variety of GNN operators that allow for operating on all kinds of graphs. And what operator is the most suitable certainly depends on the input. And as a rule of thumb, it's always a good idea to use all the information that exists in the graph to pass messages. So if there exist multiple edge types or rich edge features, one should incorporate them into the message passing scheme. In particular, sending messages based on a transformation that is dependent on the edge features provides, in my opinion, the best analogy to classical GNNs. So, to recap, features in a CNN are transformed differently dependent on whether the pixel is, for example, in the top right corner or in the bottom right corner. And we can remodel this behavior in graphs in case our edges hold information about the spatial relation between neighboring nodes. And with this, we learn a continuous filter instead of a discrete one. And we can use this filter or those filters for tasks such as 3D shape analysis. For example, to find the nose in a 3D human face. Okay, so in the next few minutes, I would like to address an evolving topic that can be framed as relational structure discovery, which recently got a lot of attention from the community since it allows us to better model our world. So previously, I made a crucial assumption, and that assumption is that we did exactly know about what the nodes and edges in our graph are. So basically, we were given a graph and just wanted to apply some machine learning on it. However, this is not always the case, and there are basically two scenarios that are complementary to working with graph neural networks. And the first question asks, what if we have incomplete knowledge about relation? And this task can be tackled by the task of link prediction. So in this case, you have an incomplete graph and you want to infer the missing links in the graph. This gets a bit more interesting in case you know only about the objects or nodes in a scene, but you have no knowledge about the relationship of those nodes. And this problem is typically referred to as relational inference, where you want to infer all the links from scratch. And the second question is, what if we do not even know about the nodes? So for example, we are given a scene that evolves over time, and we want to learn about objects, entities, or events in this scene, and in particular how they relate to each other to make a better prediction for the next time frame. Okay, so let us look at this now. For example, consider this scene of cars on a road, and we want to predict the next time step of this scene. So there are two different views to look at these problems, and they can be framed as unstructured world model and structured world model. In the unstructured world model, we are given this image and we try to encode it into an embedding from which the scene can be reconstructed. And this embedding can potentially be derived by a convolutional neural network. And we frame this embedding C1 here. And given an optional action and this latent embedding C1, we are asked to frame a prediction for the next time step, which we can learn through a transitional model which gets the embedding as input and outputs an embedding of the next time frame. It's important to note that this representation is fully distributed but unstructured. So it's basically just a vector, and we assume that we compress all of the necessary information of the observation into this single representation. The structured world model, on the other hand, assumes that our world is structured and that objects and entities are in interaction with each other. And then here again we take an observation at time step t equals 1 and pass it to an encoder. However, this representation is different since we structure it as a set of latent variables. So here we have, for example, n elements, and then each element can represent a single object of the input. And to derive the next time step, we again pass the latent representation through a transition model. But this transition model is different too, since it now takes as input a set of latent variables, and can model their interactions to make the predictions for the object. Okay, so the basic architecture for training structured world models looks as follows. We have an observation at time step t, and we begin by extracting objects using an encoder module. And this object extractor is typically modeled as a convolutional neural network, which outputs a feature map for each object found in the observation. And this feature map is further compressed by an object encoder, which maps each feature map into a low-dimensional vector CT, resulting in a set of vectors describing objects. And the transition model can now learn to model the pairwise interaction between objects using a graph neural network on the fully connected graph. And this graph neural network derives at an explanation for the next time step. So both the encoder and the transition model are trained end-to-end based on a contrastive loss, given the ground truth next hidden state and a random state from the dataset. And the cool thing about that formulation is that this network behaves in a fully self-supervised fashion, which basically means that the model learns about objects and their interactions completely on its own without any further supervision. And another advantage of this model is that it can be trained directly in latent space without any decoding or reconstruction taking place. And this allows the model to avoid modeling task-irrelevant details. For example, for certain prediction tasks, it might not be necessary to model colors, background, or patterns of objects, but we just care about their dynamics. Okay, so now I want to talk about implementing and training GNNs, which is a fairly important topic to cover in my opinion, since there are some crucial differences in contrast to working on images and sequences. And though most of these differences stem from the fact that modern deep learning frameworks are heavily designed for operating on dense representations. So in this part, I will cover some basic topics like how can we achieve effective parallelization on irregular and sparse graphs, and how can we implement mini-batching capabilities when operating on a dataset of graphs with potentially different sizes. And last, you will learn about the PyTorch Geometric library, which is an extension to PyTorch for deep learning on graphs. Okay, so consider that we are given a graph and that the representation of this graph is sparse. And so this graph is defined by a node feature matrix X, which holds the node features for the nodes in our graph. And the graph is further defined by its edge indices, I, which store for each edge in the graph its source and target node index. And so this edge index format has a shape of 2 times the number of edges. And furthermore, we may are given optional edge features that store a feature vector for all the edges in our graph. So to represent the graph on the left, we have a node feature matrix which contains 4 feature vectors for the 4 nodes in our graph. And we can represent I, the edge indices, as shown below. So for example, since there exists an edge from node 2 to node 1, the edge index matrix stored the pair 2, 1 in its first column. Okay, so how do we apply a general form of message passing on this given graph representation? And one very convenient approach is to lift the node representations into an edge parallel space, in which we can compute the messages sent along each edge in parallel. And this operation is known as the gather operation on the GPU. So here, gather looks at the indices of source and target nodes and maps each node representation to an edge representation. After computing the messages sent along each edge, we need a way to aggregate these messages back into the node space. And this operation is typically known as a scatter operation. This scatter operation now takes in the target node indices of an edge, or all edges, and use them to aggregate the messages together that are part of the same destination. The scatter operation provides different reduced functionalities, and we may have the option to aggregate messages based on taking the sum, taking the mean, or taking the maximum of values. And last, we can update the node representations by implementing the update function. And as you can see, this implementation is very flexible, since it disentangles the message, aggregate, and update functions from the message passing scheme. And that is really convenient when doing research on GNNs. Okay, so next I want to talk about mini-batch handling in GNNs. And there exists a major difference here in contrast to, for example, batching in convolutional neural networks. To recap, in GNNs, you have a designated batch dimension, and that basically assumes or requires images to have the same input dimension. And for graphs, that is not applicable at all, since graphs can have naturally potentially different sizes. So one way around this problem would be to pad the graphs with fake nodes, but this also complicates the implementation and would result in a lot of unused fake nodes. A better way to handle mini batches in GNN is the following procedure. So for GNNs, we can represent the distinct graphs in a mini batch as a single giant graph with disconnected subgraphs. And this can be achieved by stacking the adjacency matrices of the graph in a diagonal form and concatenating node representations vertically. And the main advantage of this scheme is that the GNN does not need to handle the different cases, whether it's trained in a mini-batch fashion or not. Since GNNs aggregate neighborhood information from their direct neighbors, there's no way that the disconnected graphs in our mini-batch can receive a message from another graph. And furthermore, there is no additional memory or computation overhead required to operate on this mini-batching procedure. So for example, we do not need to pad the graphs to the same length, and since adjacency matrices are stored in a sparse representation, there is no additional memory required to stack them. And furthermore, this scheme naturally supports examples of different sizes. However, one needs to take care when applying readout functions on the node representations to obtain a global graph representation. And here, since we no longer have a distinct batch dimension, we need an additional vector which tells us which node belongs to which example. And this is indicated here by this assignment vector. So for applying readout functions, one would now take in the output node representations in conjunction with this assignment vector to obtain global graph representation for each graph in the mini batch. Okay, so now that you know how to compute a round of message passing and how to form mini batches of a set of graphs, I want to introduce you to the PyTorch Geometric library, which is a Python library built upon the popular deep learning framework. And it is designed to enable deep learning on graphs directly in PyTorch. So the PyTorch Geometric library comes with the following features. It simplifies implementing and working with graph neural networks by providing a simple-to-use message passing API. It omits the need of rewriting common logic, and that may include GNN operators, loading and working with datasets, or taking care of the previously presented mini-batch approach. And last but not least, it bundles fast implementations from a variety of published papers into a unified framework, so that it helps users to apply GNNs to a specific problem where relational learning might be important. And it is in particular useful for researchers to compare their approaches to related ones and to make research overall more reproducible. So to this date, PyTorch Geometric bundles a wide range of different GNN operators that are all built based on different insights and inputs. So there exist GNN operators that can operate on graphs with different edge types, and there exist operators that can make use of multidimensional edge features. PyTorch Geometric also provides a variety of pooling operators and complete models, with some of them even being pre-trained on a specific dataset. And furthermore, it provides a lot of useful utilities, for example, to scale GNNs up, for normalization, or to explain the output predictions made by a GNN. Okay, so let us now look at an example on how to use PyTorch Geometric in practice. And I will try to present that as easily as possible, but there might be a kind of steep learning curve if you have never implemented a deep neural network in PyTorch before. Okay, so the first action is that we need to load our data into PyTorch Geometric. And luckily, PyTorch Geometric already provides most of the commonly used datasets in research. But if you want to implement your own datasets, there are a lot of utilities to help you out. Okay, so let us load a predefined PyTorch Geometric dataset. And for this, we load the PPI dataset, which holds 24 graphs, which describe protein-protein interactions, and 20 of those graphs are typically used as training graphs. So PyTorch Geometric will automatically download the respective dataset and store them on disk, so that's really convenient. So now we can inspect this dataset, for example by printing the overall dataset information and printing the first graph inside the dataset. And here we can see that this dataset indeed holds the 20 training graphs. And we can see that a graph is stored inside a data container, and that the information about what is present in this graph is nicely laid out to us. So we can see that the graph contains the edge index matrix mentioned earlier, which is here a matrix of shape 2 times the number of edges. And we can see that the graph comes with a node feature matrix X and ground truth labels for each of its nodes. So here the first graph holds the information of around 1,700 nodes, and each node has a 50-dimensional node feature matrix or vector, and the task is to predict the existence of around 120 labels. We can use the data loader class to create mini batches of this dataset. So here we would create mini batches of size 2, and we want our mini batches to be created randomly by setting the shuffle option to true. Okay, so now we can inspect the first element provided by our data loader. And we can see that we no longer get a single data object back, but instead we get a batch object. So there exists now around 3,400 nodes in our supergraph, and the number of edges also increased. And we can see that this batch object now holds an additional attribute which is named batch, which basically just models the assignment vector mentioned previously. And that is, it holds the information about which node belongs to which example. Okay, so having our data ready to use, we can construct a simple network architecture to learn from this dataset. And here we make use of the GCN-conf, which is one of the most basic and simple GNN operators in literature. Okay, so defining a network is really straightforward if you are familiar with PyTorch. So we first need to initialize the GNN operators that we want to use in our network. And here the arguments passed to creating the GCN-conf describe the input and output feature dimensionality of nodes. So here our first GNN operator expects as input dimensionality the number of node features in our dataset, and it will map those to a hidden dimensionality of 256. And next, we want to apply a second round of message passing, and therefore we create another operator, and this time this maps from the hidden dimensionality to the number of classes. Okay, so with this we need to define the forward computation of our model, and here we get the node feature matrix X and the edge connectivity matrix edge index as input, and we simply stack the two GNN operators to compute the output node embedding. And between those two rounds of message passing, we apply a ReLU nonlinear activation function. Okay, so with this we have everything ready to train our model. So we first initialize it and send it to the GPU, and we create an optimizer that takes in the model parameters, a learning rate, and its task is to update the model parameters based on their gradients after each round of forward pass. So training a GNN model is then really similar to training any other model in PyTorch. We iterate over our data and send it to the GPU, and next we compute the output of the model for the specific mini batch. We can use this output to compute the loss based on the ground truth node labels, and we can use this loss further to compute the gradients of the model parameters. And those gradients can then be used to update the parameters. Okay, so that is all it takes to implement a simple GNN from scratch. Next, let's look at how one would make PyTorch Geometric scale to giant graphs. So consider the case where you have a single giant graph, and for graphs which are really big, you may encounter a runtime error saying that Qdo is out of memory. But luckily, PyTorch Geometric comes with some utilities to enable learning on those giant graphs. And here we make use of the cluster GCN approach, which is a method based on partitioning the giant graph into multiple subgraphs, which can then be processed in a mini-batch fashion. And so for converting a giant graph into a number of partitions, all you need to do is creating a partitioning loader that will first partition the graph into a number of clusters and will then provide mini batches of those clusters. And the only change to train our model is that we now need to iterate over the loader and process the graph in mini batches. And as you can see, scaling GNNs up with PyTorch Geometric is really straightforward and only requires a few lines of code change. PyTorch Geometric also comes with some utilities for creating your own message passing layers. For this, we can inherit from the message passing class. And in its constructor, we can say which type of aggregation we want to apply. And here we opt for a simple sum or add aggregation. The forward pass now defines our message passing computation. And here we can start propagating messages by calling the self.propagate function. And this function takes in the edge connectivity named as edge index and all other information that is needed for propagation. And here, as a simple example, we pass in the node features x as well as the edge weights of each edge. This propagate function will internally call the message function, where you can define the messages that are sent to each destination node. And here, node features get automatically lifted to source and target nodes. And we use _j for the neighboring nodes and _i for the central node that receives those messages. And here our message computation is rather trivial, where we just scale all neighboring node features by their corresponding edge weight. Okay, so to conclude, PyTorch Geometric provides uniform implementations of over 40 GNN operators and models, which might be suitable for different learning tasks. It is also extendable by using a simple message passing interface. And overall, it provides access to over 100 benchmark datasets, which will get downloaded automatically. It provides an automatic mini-batching procedure, both for operating on a dataset of graphs as well as operating on a single giant graph. And it further provides a variety of pooling operators and readout functions. And it comes also with some useful transforms such as augmentation or point sampling. And overall, PyTorch Geometric is pretty fast, and we achieve that by making use of dedicated CUDA implementations. So if you're interested in learning more about GNNs and applying it to your own problems, please feel free to check PyTorch Geometric out, which is fully open sourced on GitHub. I also recently added some collab notebooks to PyTorch Geometric, which interactively introduce you to the library, and you can easily access them by visiting the PyTorch Geometric GitHub page. And as an example, I will now run through the first notebook together with you. Okay, so let's visit the PyTorch Geometric GitHub page and click on the Google Colab notebook link in the README. And here we will accept the first one, which is named Introduction Hands-on Graph Neural Networks. And we can run the first code block here to download and install PyTorch Geometric, which should take around 1 minute at max. Okay, so this introduction is based on a simple graph structured example, the Karate Club network, which describes a social network of 34 members of a karate club and documents links between its members who interacted outside of the club. And here we are interested in detecting communities that arise from the members' interactions. We can easily access this dataset in PyTorch Geometric and inspect it by importing it. And by running the code, we will see that this dataset holds exactly one graph, and each node has a 34-dimensional node feature vector, and this dataset comes with 4 classes, which correspond to our communities. So we can load this graph by grabbing it from the dataset and also inspect it. And here we can see that this graph holds 34 nodes and 156 edges, which results in an average node degree of around 5.6. We can also see that this dataset comes with 4 nodes that can be used for training, and that puts us at a labor rate of around 12%. And here the task is to infer the community assignments of the remaining nodes. The data object also comes with some utility functions where we can see that there do not exist any isolated nodes, there exist no self-loops in our graph, and this graph is an undirected one. We can also print out the edge index, where we can see a list of pairs of node indices, which describes our edges inside of our graph. And here we can see that, for example, that node 0 is connected to numerous other nodes like node 1, node 2, and so on. We can also visualize our graph by converting it into the Network X library, which is a fairly popular library for graph manipulation and visualization in Python. And so we can make use of the toNetworkX function to convert our data object and visualize it afterwards. Okay, so let us now implement a graph neural network that tries to infer the cluster assignments of the remaining nodes. And here we make use of 3 GCN layers, which are stacked and enhanced by the 10H nonlinearity function. And since this is a fairly easy task, our GCN produces only a 2-dimensional node embedding for each node. And that comes with the advantage that we can easily visualize the outputs produced by our GNN. And after that, or after obtaining the node embeddings, we apply a final classifier that maps the 2-dimensional node embeddings to one of the 4 classes. Okay, so we can run that code and print our model out, and we can see that it exactly contains our 3 convolutional layers and the final classifier. Okay, so let us now look at the embeddings produced by our non-trained GNN, where all the parameters are completely initialized at random. And interestingly, we can already see that the model produces an embedding of nodes that closely resemble the community structure of the graph, where nodes with the same color are already clustered tightly together. But we can certainly do better by training our model. So for this, we create a training function which takes in the data object, and it runs the forward pass through the model. It computes its loss based on the training nodes, and based on the loss, it computes the gradients for the parameters and uses the optimizer to update the parameters of our model. And run this training loop for 400 times and visualize the node embeddings as we go. So let's run that now. And as you can see, our 3-layer GNN model manages to linearly separating the communities and classifying most of the nodes correctly, except for some green nodes and some yellow nodes. And we did this all with a few lines of code thanks to the PyTorch Geometric library, which helped us out with data handling and GNN implementations. Okay, so that was the run-through of the first Google Colab notebook, which embed the Karate Club network. And as a small exercise, I want you to run through and complete the point cloud classification Colab notebook if you're interested. Of course, you can also experiment with the other Colabs as well. Okay, so thanks for watching and see you at the Q&A session. Bye.